The next topic we want to talk about is centripetal force. Now, that is, of course, going to be the force that's involved with the centripetal acceleration. And hopefully you'll remember that centripetal acceleration is the kind of acceleration you get when something is turning. And so, if you'll remember, when you have a velocity and the force is perpendicular to the velocity, that will create an acceleration that is perpendicular to the velocity, and that is, of course, the kind of acceleration that will cause it to turn. Any acceleration that's along the velocity will cause it to either speed up or slow down, but any acceleration that's perpendicular to the velocity will cause it to turn. And that is, of course, a centripetal acceleration, and that is caused by a centripetal force. Now, as we've talked about previously, the centripetal acceleration, the acceleration that comes from going in a circle, has a magnitude of the speed squared divided by the radius of the circle. And if you remember, the acceleration also points towards the center of the circle. The velocity vector is going to be tangent to the circle. And generally, when we talk about centripetal acceleration, we usually are keeping the speed constant. Of course, if the speed is increasing or decreasing, you would have a tangential acceleration, which would increase the length of the velocity vector or decrease it if it was in the opposite direction. But the centripetal part of the acceleration is always going to point towards the center of the circle. And in order to have a centripetal acceleration, you need a force that's pointing towards the center of the circle. And so here's an example that you could have a centripetal force. Imagine a string that's being swung in a circle. And so the string is going to have a tension that's pulling back towards the center of the circle, and that tension is what's going to be creating the force that's changing the direction. So this guy's going to be going in a circle over and over again. Now, if the string were to break or be cut, the object is going to go tangentially, because the velocity vector is tangential. And Newton's first law says things want to keep the velocity they have. But what keeps the thing from going off tangentially and keeps it in the circular path is the fact that there's this force always pulling it towards the circle. In this case, the centripetal force is the tension. Okay, let's look at an example. Our example is a 25-meter long rope can be sustained a maximum tension of 16 newtons before breaking. The end of the rope is attached to a 0.45 kilogram mass, and the question is, what is the fastest speed that it can be swung in a circle with without breaking? Now, of course, this is going to be similar to the picture we had in the previous slide. I've got a mass at the end of a string, and it is being swung in a circle. And we're going to ignore anything else that might be acting on this mass. So we're going to say there's no gravity or anything to worry about, because the problem just says we're just dealing with the tension in the rope. So the tension, that's the centripetal force, and that's going to be equal to mass times acceleration. But the acceleration for centripetal acceleration is v squared over r. Anytime something is moving in a circle, you should immediately think the acceleration is v squared over r. Really, not just a circle, any curved path, but especially for a circle. Now, all we have to do is solve for the velocity, and then we're going to plug in the maximum tension that the string can sustain, and all the other parameters, we just plug them in. And when we calculate everything, we get that the speed is 3 meters per second. And it's that easy, centripetal force. Now here's another example. We have a 1,500 kilogram car rounding a curve on a flat road with a radius of 25 meters. And so this is basically a car doing a donut. It's just going on a flat surface and it's making a circle, but it's making a really wide circle. The radius of the circle is 25 meters, and the speed is given to be 15 meters per second. Now the question is, what coefficient of friction is needed to keep the car from skidding, or from sliding, basically? And so here we have our picture that I've drawn here. So the picture of the car, we've got two pictures here. The first one on the left is sort of the head-on view of the car. And you can see that we know that the car is moving in a circle. And so if we look to the right, we see this top-down view. The car is moving in a circular path. The velocity is going to be tangent to the circle, and the force of friction is what's supplying the centripetal force. Previously it was the tension, now it's the friction. So the friction has got to be pointing towards the center of the circle. So if we look at our head-on view, we know that the normal force and gravity are going to be the forces in the y direction, and the friction, if we take this as a snapshot, is going to point in the x direction. And of course we can draw in our normal coordinate systems, x, y, to indicate that. Now we know the weight of the car is just going to be m times little g, and we can plug those numbers in and we get 1.44 times 10 to the 5th newtons. I've expressed that in scientific notation because it's a pretty big number. And in the vertical direction, we know that the sum of the forces is going to be the normal force minus mg equal to 0 because there's no acceleration in the y direction. And so that implies that the weight is the normal force, so we know the normal force is 1.44 times 10 to the 5th newtons. And just to be clear here, what we've really done here is this is the sum of the forces in the y direction. So what are we going to do next? We're going to do the sum of the forces in the x direction. So here we have the sum of the forces in the x direction, and there's only one, it's the friction. And so the sum of the forces in the x direction are going to be m times a, and of course this here, that is the centripetal acceleration that we're talking about. And we can just plug in the values. So we have 1,500 kilograms, 15 meters per second, quantity squared, divided by the radius, 25 meters. And when you plug that in, you get the force of friction is going to be 13,500 newtons. That's what is necessary to keep this guy moving in a circle. What would happen if the friction were less than that? If the friction were less than that, then there wouldn't be enough force to keep it moving in a circle and the car would skid. Now the problem actually asks to find the coefficient of friction, which we can use the friction formula to find that, and we're just going to solve for mu sub k. Plugging in the numbers, we get that the coefficient of friction is about 1/10. So any mu, any coefficient of friction that is bigger than that, is going to provide enough force to keep the car on the road and keep it from skidding. Now this next problem is a very famous physics problem. It shows up on lots of physics tests, hint hint. It shows up on the MCAT tests sometimes. It's really interesting because it involves an inclined plane, but it also isn't worked the way we normally work inclined plane problems. So first of all, what is a banked curve? So if you've ever driven like one of those big circular curves off the interstate, one of those like off ramps that are kind of in a big circle, you may notice that the ground usually isn't flat when they make those big circles coming off the interstate. Those are examples of banked curves. And so here, what we see with the triangle in this picture, this is kind of a snapshot. This triangle would actually be coming out of the page, but also making a circle. And so again, you're going to have the car, it's coming out of the page and making a big circle, but as it does, the car is tilted on this incline. So hopefully you understand the picture that I'm trying to describe here. And basically, the question is, why do people that design these curves, why do they tend to make them banked like that or tilted as you go off the on-ramp? And the reason is because that actually can make it safer. So here's the idea. You have a car, it's traveling with some velocity on this banked circular curve. Now, these people are coming off the interstate, so they may be driving a little bit faster than they should be according to the speed limit. And so this curve is going to have a radius r, and then the tilt of the road is going to be banked at the incline angle theta. Now, you could have a situation where ice, for example, on the banked curve may make the friction negligibly small. And so the question can be, what angle do you need so that the car can safely navigate or negotiate the banked curve? So let's look at our picture here with our force diagram. Now, again, in the problem, there's no friction. We're assuming that there's not even any friction on this road. And what we're going to see is that even without friction, it can be, under certain conditions, safe to navigate this curve. Now, what we have here is the weight, which is going to point straight down, and the normal force, which is going to point perpendicular to the surface, perpendicular to the tilt. Now, normally, when we have inclined plane problems, we tilt our coordinate system so that it points down the incline. But think about why we do that. We do that because usually the object is sliding either up or down the plane. Here, the object is not sliding up or down the plane, it is actually coming out of the page. And so it's not changing its orientation with respect to the bottom of the plane. It's keeping the same distance from the bottom of the plane, it's just coming out of the page and then moving around in a big circle. So we're going to keep our coordinate system in the normal up and down, left, right orientation. And that means instead of resolving mg into x and y components, we're going to have to resolve the normal force into x and y components. And you can see them in red here. We have the y component and the x component. And as we've seen before, if this is the angle theta of incline, that's going to be the angle theta between the normal force and its y component. Once we've broken the forces into x and y components like that, we can do the sum of the forces. Now, in the y direction, we have F and y, that's the y component of the normal force. We have mg, that is the weight, and those are the two forces that are in the y direction. The weight is obviously negative. The y component of the normal force is pointing up, so it's positive. And so when we do the sum of the forces in the y direction, we get the y component of the normal force minus mg equals to 0. And that tells us that the y component of the normal force is equal to mg. But of course, we know that because of the picture, this is just going to be Fn times the cosine of the angle theta. Because this is the adjacent side to that angle, it's going to go with cosine. And so we can say that Fn cosine of theta equals mg, and then we can solve for the normal force here. And it's going to be mg actually divided by the cosine of the angle. And so that's the normal force, and we got that by doing the sum of the forces in the y direction. You probably guessed the next thing that we want to do is get the sum of the forces in the x direction. And there's only this one, the x component of the normal force. And so that's going to be equal to m times a, where a is the x component of the acceleration, but our circle is going out of the page and over this way. So this is actually the part of the force that's pointing towards the center of the circle. And so that tells us that that's the force that's providing the centripetal acceleration. And so that's going to be v squared over r. So we can say Fn is equal to m times v squared over r. That is the a sub x. Plugging in here, we get this little symbol with the three dots. That means therefore. So we can say therefore the x component of the normal force equals m v squared over r. And of course, that's going to go as the sine of theta. And I could see that maybe more easily by drawing the x component up here and seeing that that's the opposite side of the triangle, but we drew it kind of parallelogram style down at the bottom. But either way, that's going to be the component that goes with the sine of theta, and so we can plug in. Now, this Fn we solved for in the previous slide, so we can plug that into there. So we can do that here. We've got, in the previous slide, we said Fn sine of theta equals mv squared over r, but a couple of slides ago we saw that Fn was mg divided by the cosine of theta. We can plug that in directly. We can also see that sine divided by cosine is going to be tangent, and we're going to see the m's are going to cancel, and then I'm going to move the g over to the other side of the equation, and I'm left with the tangent of theta equals v squared over gr, and to find theta, I get the arctangent of v squared over gr. And what is that? That is the angle for which the normal force alone can provide the force necessary to keep the car moving in a circular path. In other words, even if there's ice on the road, even if there's no friction, simply by banking the curve, you can help prevent the car from skidding out and having an accident. So that's kind of cool. And of course, if the problem had been to find the velocity or to find the radius, you just do the algebra and solve for whatever you were looking for. The approach of doing the problem would be the same thing. Okay, here's another example. This is called the conical pendulum. Now usually when you have a pendulum, it swings back and forth in a plane, but this is a pendulum that's actually swinging in a way that's tracing out a circle, kind of like a tether ball. Anyway, what we have is the pendulum has a length L, bob, that's the ball or whatever it is at the end of the string, of mass m, and it rotates in a horizontal circle as shown. The length of wire for the pendulum makes a constant angle theta with respect to the pole or the vertical axis, and it has a constant speed v around the circle. So let's look at the picture here. We've got the radius of the circle that's being traced out, and the velocity is tangent to the circle, and so that's going to be given by that. And the v, of course, represents the speed, which is constant. Now, the ball has got two forces on it. There's no friction. We're going to ignore air resistance. There's only the weight and the tension in the rope. And the tension, of course, is along the length of the rope, so it's going to be directed at that angle. So over here, we have a free body diagram. Remember free body diagrams? That's where you take the forces acting on an object and you break them into x and y components isolated. And so our tension is going to break into a y component of the tension and an x component of the tension. And if this is the angle theta, if I draw this up here, that also would be the angle theta. So that's why you can see that that's going to be theta there. And so we can now apply the sum of the forces in the y direction, which would be those two forces, and the sum of the forces in the x direction, which would be that force. So the first thing that we can note is that there's no acceleration in the y direction. This ball is not going to be leaping up or down. It's maintained in this horizontal plane of this horizontal circle. And so the acceleration in the y direction is going to be 0, and so the sum of the forces is equal to 0. And of course, the sum of the forces is just ty minus mg, where ty is going to be t times the cosine of the angle. Why cosine? Because that's the adjacent side to the angle. And of course, if I drew my tx to make a triangle, I would see that the x component goes with the sine. And that's what we have here. Tx is t sine of theta. Now that's not got a 0 acceleration, that's got a centripetal acceleration, and so it's equal to mv squared over r, where v squared over r is the centripetal acceleration. Okay, so what we have here is this is from the y equation, and this is from the x equation. And from the y equation, we got that t times the cosine of theta equals mg, and that lets us solve for the tension, which is going to be mg divided by the cosine of theta. And that was what the first part of the problem asked us to find. It said, find the tension. The other thing it asked is the period of rotation of the ball. How long does it take for the ball to complete one circle? And so we can apply the x equation for that. We can say that t sine of theta is equal to mv squared over r. That's what we saw on the previous slide. But if I take this t and plug it in, so this t gets plugged into there, and of course that's just mg over cosine of theta for t. So this right there is the tension. And we can note that the mass is going to cancel. Sine over cosine is tangent. And so we're left with g times the tangent of theta is v squared over r. Now we want the period of the motion. And the period of the motion, so this guy's going in a circle, and it's got a circle of radius r, and it's going to have some velocity, or some speed. What is speed? Speed is just distance over time. The distance of the circle is going to be 2 pi times the radius, and the period is the time. So this is distance over time, or period, and this is, of course, the speed. And so that just comes from the definition of speed. We're looking for the period. it's not obvious that you would need the speed to do that. So that's why, you just got to see a lot of these examples so that you can see all the different things you can do with them. But plugging in those values, you can say, okay, and of course, 2 pi r over the period, that was the velocity, or rather the speed, sorry. And so we're looking to solve for the period, and so when we do that, we get this equation that's boxed here. There's just some algebra to get to there, but I think you guys can all do that algebra. And that is exactly what we are looking for in the problem. That's the time it takes for the ball to make one complete circle.